This is VLSI data conversion circuits, lecture 21. In the last class, we were wondering about the distribution of the error at the input to the quantizer. And we said that if we assume that the quantizer is an additive noise source, and the input to the quantizer can be written as the sum of the input to the modulator, right, plus NTF of Z minus 1 times E of Z, right. And we were wondering how this animal behaves, and by assumption this corresponds to a uniformly distributed noise sequence, which is white, which means that it is uncorrelated from sample to sample and so on. In the time domain, this corresponds to the convolution of E of n with a filter whose impulse response is h of n minus delta of n, correct. Let us call this h 1 of n, just not to keep carrying h minus delta all over the place. So, the output is, since this is a convolution, is E of k h of h 1 of n minus k equals 0 to infinity, right, or 0 to n, I suppose so, all right. So, this is the expression for the noise process which is riding over the input at the input to the quantizer. Okay. Now, to find a bound on this, what do you think you can do? Please recall that E of k is less than or equal to delta by 2. So, if this is the noise process riding over the input, it must follow that this must be less than or equal to sigma k equal to 0 to infinity delta by 2 times modulus of n minus k, correct. I mean A B is less than mod A mod B, correct, and mod A is less than delta by 2. So, this bound is equal to delta by 2 plus minus k equal to 0 to infinity mod h 1 of n. Correct. So, what is this telling you? I mean, let us say you compare the first order and the second order modulators. What is mod h 1 of n in the first order modulator? It is 1. In the second order modulator, it is 3. Okay, all right. And as we will go along, we will see, I mean, how we came from the first order to the second order modulator can be repeated again, and you will get a third order modulator where the noise transfer function becomes 1 minus z inverse whole to the 3, correct, and you are expecting to do much better in band and worse out of band, because so for example an NTF which is 1 minus z inverse the whole cube, right, h of n is what, 1 minus 3 minus 1, the sum must be 0, okay. So h1 of n therefore will be 0 minus 3 and minus 1. So what is the upper bound on the noise process riding over the modulator input at the input to the quantizer? 7 delta by 2, okay. So as we, so first order, second order, third order, okay, sigma h1 is 1 for the first order, 3 for the second order, and 7 for the third order. And what is the out of band gain, or rather the gain at pi? For the first order it is 2, for the second order it is 4, for the third order it is 8. And what can you say about sigma h square of n? Or let me say sigma h1 square of n. In this case it is 1, in the second order example it is 5, in 19, okay. And please note that the square root of sigma h1 square of n, and this gives you this times delta square by 12 is the variance of noise to the input to the quantizer, correct, all right, and this will and the square root of this must be significantly smaller than the absolute upper bound. Is that clear? Okay. So I mean, what do you notice as far as the trend here is concerned? As you go from first order to second order to third order, what is happening to the in band noise? In band noise is going down. What is happening to the out of band noise, that is the band noise at high frequencies? The high frequency noises is going up, okay. And what can you say about the variance of the noise at the input to the quantizer inside the loop? Is also going up. Is this clear? All right. So as I said, since we see improvement from first to second and second to third order modulators, the obvious question that arises is why can't I continue this ad infinitum, correct? And in general I will therefore end up with a noise transfer function which is of the form 1 minus z inverse whole to the n. So the in band noise will be of the form what will be the integrated in band noise? Will be proportional to OSR. See 1 minus z inverse to the n means that the noise transfer function at low frequencies goes as omega to the n. So, when you square it you will get omega to the 2n, when you integrate it you get 2n plus 1. So, this must go as OSR to the power minus 2n plus 1. So, which is therefore how many bits per every doubling of the OSR? N plus half bits per every of the OSR. Right. And as we saw during the last class, the input to the quantizer is noisy with the transfer function from the quantizer noise process to the input of the quantizer being NTF of z minus 1. And in the second order case, if we kind of said, okay, why do not we assume that it is Gaussian, because it seems to be high in the middle and kind of tapering off towards the ends, right. We of course realize that it cannot be truly Gaussian, because this is bounded, whereas a true Gaussian is not bounded, all right. Yet a Gaussian is a good approximation, and there is, it is not just fancy, but you must understand that E of n is assumed at least to be a white sequence, in other words uncorrelated from sample to sample. The shaped quantization noise is formed by taking this white sequence and passing it through a filter, right, which means that at any one instant of time or at any one sample is a linear combination of several samples of the quantization noise, correct, because the output, the input to the quantizer is a convolution of E of k, which is the quantization noise sequence, with some filter transfer function, and E itself is uncorrelated from sample to sample, and the input to the quantizer is simply a sum of several of these uncorrelated random variables. So, if you take many random variables with uncorrelated random variables with the same distribution and you add them together, correct, what can you say about their probability distribution function? If you take a large number of these samples and then go on adding stuff together, eventually by central limit they will the sum will have a cumulative distribution function, which is the integral of the Gaussian, which in this case turns out to be equivalent to saying that the PDF will tend to Gaussian, right. There is a big difference between tending to Gaussian and being Gaussian, right, and this is the difference, okay, all right. One, of course, we know for sure that it is bounded, so it can never really get Gaussian unless you have a large number of terms and so on, infinite number of terms in fact. But as I said, everything that is probably needs to be known about a Gaussian is known. So, it is a very useful approximation to make, right. So, that we can now exploit all the knowledge that has been developed over the generations on Gaussian processes and what happens to Gaussian processes as they are processed, either linearly or non-linearly, you understand. So, that is the intuition, at least for assuming that the shaped quantization noise, not quantization noise is still uniform, right, but once you pass this through a filter where with a reasonably large number of coefficients, you start adding up various uncorrelated random variables and the result starts to look like a random variable whose PDF is Gaussian. Okay. All right. So, as we just saw, increasing the order of the loop seems to be giving us better and better and better results. So, the question is what really, I mean, it sounds too simple, right. So, you just go on adding integrators and you can make a very, very bad quantizer look like a quantizer which is extremely good. So, there must be a, if I were an engineer I would say this sounds too good to be true. So, it must break at some point and the question is where, right, and why of course. So, now we will take a look at why this assumption is not, I mean you can't go on putting integrators in the loop, right, going on increasing the order of the noise transfer functions and make, in other words, 1 minus z inverse to the n, where n is a large number, with the motivation being that you want to reduce the in-band noise, is not quite a viable thing in practice, and we will now go ahead and discuss this. Before I proceed, I would like to remind you that the out of band gain of this noise transfer function is 2 to the n, right, and as we go on increasing the out of band gain, what can you say about the variance of the noise at the input to the quantizer? It goes on increasing, correct. We saw going from first order to second order to third order that the variance of the noise at the input to the quantizer went up from delta square by 12 to 5 delta square by 12 to 19 delta square by 12. So, you can only imagine what happens when you make a fourth order modulator. What is sigma h1 for a fourth order case? 14641, you remove the 1. So, it is 15, all right. What is the gain at pi? Is 16, and what is sigma h1 square? Is 16 plus 36 plus 16 plus 1, which is 69, okay. So, you can see that the variance of the noise at the input of the quantizer is increasing very rapidly indeed, and that makes sense because the out of band gain is, or the gain at pi or at high frequencies is dramatically higher, and the variance of the noise is proportional to the square of the gain, right. So, it makes sense that the variance of noise has increased by a large factor, okay. In fact, I mean if you kind of think of this, see most of the gain, the energy in the NTF minus 1 is coming from which frequencies? Coming from high frequencies. What has happened to the high frequency gain? Has gone up by a factor of from 8 to 16 has gone up by a factor of 2. So, if most of the energy is coming from around pi, what must you expect for the variance of the noise? Should go up by a factor of 4, and what are you seeing? One is 19 delta square by 12, the other one is 69 delta square by 12, right. Indeed, it is very close to 4, and from 5 to 19 again it is close to 4, 1 to 5 is again close to 4. You understand? Is this clear? The intuition behind the stuff increasing by a factor of 4 every time is that most of this energy is coming from high frequencies, the high frequency gain is doubling every time. So, it makes sense that it keeps increasing by a factor of 4 every time. Okay. So, increasing the order of the noise transfer function, right, to 1 minus z inverse to the n very quickly causes the input to the quantizer to have a noise whose variation goes on increasing very rapidly with n, right. Now, the question is, what does this do to the modulator loop as such? Okay. We must remember that the quantizer has a finite range. Beyond a certain range, the output of the quantizer is saturating. The range of the staircase is not infinite. Okay. So, let me drive home that point. Okay. So, this is the range of the quantizer, beyond which the output of the quantizer simply saturates to some value, correct. Now, let us understand what happens when such a quantizer is embedded inside a feedback loop. So, again I am going to assume some generic loop filter, say L of z. For a given noise transfer function, you can calculate L of z by using, how is L of z related to the noise transfer function? One by 1 plus L of z is the noise transfer function. Okay. And this is V, this is Y, this is U. Now, let us assume that U is purely DC. Okay. So, Y therefore will be, how will the waveform at Y look like? It's a constant sequence. So, how do you think Y will look like? It will look like some DC level, on top of which there will be noise, some noise will be riding on top of this DC quantity, correct. And we understand that the variance of this noise will keep increasing as the noise transfer function's gain at high frequencies goes on increasing, all right. So, this is the actual input into the quantizer, correct, and the output of this quantizer is a quantized version of this input, which is DC plus some noise. Okay, it is a nonlinear function of DC plus some noise. alright. And see, dealing with linear systems is hard enough, okay. So you can imagine that dealing with nonlinear systems is a lot harder, especially when they are enclosed in feedback loops. So a natural way of solving this problem is to, what do you think you do? I mean, imagine you were a researcher in the beginning of the 20th century where a lot of the linear stuff was figured out, but then you started encountering systems with nonlinearity. So what do you think you might do? So reasonable thing to say is, okay, let me try and see if I can use my knowledge of whatever I have learned in a linear control systems class, which is all the various stability criteria and all that, which are only applicable to linear systems. Let me see if I can somehow hack a nonlinear system and in a manner so that I will still be able to apply my theory which was designed for linear systems, okay. So in this system, which is a linear loop filter followed by a nonlinearity, what should I do? I mean, I should try and eliminate nonlinearity. So what would I do? I will try and approximate the only nonlinear element in the picture, which is the quantizer by a linear block, correct. So in other words, I say that I understand that y is composed of two components, right. One is y dc, and why is y dc there? Because the input is dc, okay. Y dc plus, let me call this n1, where n1 corresponds to the shaped quantization noise which is floating around in the loop, correct. The output, so the input to the quantizer is y, which is y dc plus n1. The output of the quantizer is v, right. So this goes in through a quantizer and the output is v, okay. So what do you think I can do to approximate the quantizer as a linear block? Okay, and okay. So what you can do is say, okay, I have this box, right. I have some output v, I do not know what is inside the box. I have two inputs y dc and n1 and one output v. I want to find a linear approximation to this box, okay, alright. If this was truly a linear box, then if q was linear, then what does it mean? V must be some k1 times y dc plus k2 times n1, correct, right. If you had a, let me rephrase or repeat the argument again. I have a box with two inputs y dc and n1 and one output v, alright. If this box was truly linear, then the output would be represented as a linear combination of the two inputs weighted here with k1 and k2, alright. And how would I find k1 and k2? Pardon? Alright. So if I was given the sequence y dc and if I was given the sequence n1 and given the sequence v, how will I find k1 and k2? no, I mean you have no choice, right. Let us say these are the recordings from some plant, okay, all right. You have y1, you have this sequence, ydc is given, n1 is given, v is given, okay, as data, and I want you to compute k1 and k2. What will you do? Okay, so if ydc and n1 was given, then I will form a column vector ydc, right, another column vector n1, this multiplied by k1 and k2 must be equal to v, where all these are ydc and 1 and v are column vectors, correct. So, in other words, if I had a sequence which was 10,000 points long, and if q was truly linear, right, then basically I need to determine k1 and k2, right. All I need are two equations, correct. So, I will take at any two instants of time, I will find, I will look at ydc, n1 and v, two equations, two variables, and I can solve, even though there are in principle 10,000 equations, correct, and all these will be linearly dependent, okay. So, when you have more equations than unknowns, the problem is under constraint, and you can find a, you can solve this equation, you will get a unique k1 and k2, all right. Now, what do you think will happen? So, this is, let me put this down here, unique k1 and k2, okay. Now, what do you think will happen when if q is not linear, then what do you think will happen? So, you cannot get, you cannot, I mean v will not be identically equal to k times ydc plus k2 times n1, there will also be some, there will be some error, correct. All right. Now, the question is, what is my best approximation to I mean of this system to a linear one?
Mean square error of e goes to 0.
So, reasonable approach is to say, okay, I cannot find, given that the system is non-linear, I cannot find a k1 and k2 such that v exactly equals k1 times ydc plus k2 times n1, you understand, all right. Then the next question is, okay, I mean that is fair enough, because this is a non-linear block. So, the next question is, okay, I know it is non-linear, so I must expect error, but can I be smart about choosing k1 and k2, and as he said, a reasonable thing to do is to choose k1 and k2 such that the mean square value of this error is as small as possible, correct. In other words, we still have this set of equations, all right, but what we need to do is to find the least squares solution to this set of equations. So, find k1 and k2 are chosen to minimize mean square error of E. You understand? And how would you find the mean square error? I mean, you know least squares, isn't it? So, if I call this matrix A, is this, yeah, so A times K, and if I call this K is V. So, the least square solution corresponds to A transpose times A times K is A transpose times V, which means K, the least square solution, will be A transpose A inverse times A transpose times V. All right. This matrix A will it be a thin tall matrix, I mean tall skinny matrix or a short fat matrix? It will be more rows than columns, which will be a tall skinny matrix. Okay. All right. So, K is the least square solution to A k equal to V. And how will you find the mean square error? You actually find A k, which is your best approximation to V, you subtract V, right, and then find its so this is basically E transpose times E gives you the sum of the squares of E, and that divided by the number of samples will give you the mean square E. Is this clear? I mean, if you do not know least squares solution to a set of equations, you can read it up, but at this point all that I want you to be aware of is that you should appreciate that it is possible to choose K1 and K2 such that the error is minimized, correct. So, this quantizer has two inputs and one output, right. So, in other words, and it is nonlinear. So, if you plot this on a I mean if you want to show this in a picture, the input versus output is a surface, right. It is a very nonlinear surface because it got steps all over the place, right. However, what we are trying to do in this linear approximation is to fit a plane to that surface, and if you have some surface and if you want to fit a plane to it, there is a way of choosing the plane such that the error is minimum. You understand? Okay. I mean, and the least square solution is just a way of computing those two coefficients K1 and K2. All right. Okay, great. Now that we know yeah, you can divide it by the number of right samples. Okay. So, now that you have L of z and you have replaced the quantizer by a block which is, please note that in general K1 need not be equal to K2, all right. Okay. So, K1 is the gain for the DC part, K2 is the gain for the noise part, and E is the error, right. So, this error what is the mean of this error? it will be 0 mean, correct, because if the error is not 0 mean, I can always what do you call choose the coefficient such that the error is 0. Now I can represent the delta sigma loop, okay, given that I have a linear approximation to the quantizer by 2 loops one which only deals with the DC path, okay, and one which only deals with this part, right. The motivation for breaking it up into these two systems is simply to, you represent the quantizer by a block which is giving one gain for DC and another gain for the noise plus adding an error, right. What is responsible for the noise? Finally what is responsible for this N1? This E itself, you understand, okay. All right, if the please recall, this is a little subtle and it takes some time, you must go back and think about this carefully and realize why this way of breaking up the modulator makes sense. You must understand that the noise N1, right, is a consequence of E. One way to appreciate that is that if the quantizer was perfectly linear, okay, there would be no N1 and there would be no E either. Is that clear, right? This whole jumping around at the input of the quantizer is coming because of quantization which is error prone, right. So it makes sense that this this N1 is a consequence of E which is going around the loop, right. And so you can break this system up into two parts. Please note that this is something that you have been always used to doing. If you have multiple inputs in a linear system, you can break it up, you can think of it as many systems, identical systems there, each with one input, correct, and there is no confusion at all because it is a linear system. The basic system remains the same, only the location of the input keeps changing. Here there are two inputs and the gain for each input is different. So the two systems will be different, okay. So this is the linear system corresponding to the input and this is the linear system which models the way quantization noise flows in the loop, all right. So this kind of analysis where you take a nonlinear system and approximate it by its linear part, okay, and some error is what is called describing function analysis. And please note that this is only only an approximation, right, where we try and use the background that we have developed in linear control systems to a problem which is non-linear and therefore presumably very difficult to tackle analytically. Okay. So, I mean you should not be surprised that I mean if you assume this and then you conclude that I mean you find after your analysis that something is fishy or weird or does not make sense, you should not be too surprised because the underlying assumption is not fundamentally correct. Okay, it is like assuming 1 equal to 2 and then you can prove that the sun goes around the earth. Okay, I mean the argument may be perfectly true from the step that you assume 1 equal to 2 and all the way up to proving the sun moves around the earth, right. Then you can say, hey, my arguments are all right, how is it that I am coming to totally wrong conclusion, and I mean no surprise because you assumed 1 equal to 2, understand. So this is only a weird, I mean this is only an attempt to understand a horribly nonlinear system where it is most likely not possible to get analytic solutions by using stuff that we know from linear systems, you understand. And this is a very routine thing that was I mean that is used in nonlinear control systems, and it works quite well in many systems, though one should be surprised one should not be surprised that it does not work in several classes of systems. Okay. All right. Now given that we are armed with this new knowledge, let us kind of look at what happens in a real quantizer. Okay. I have taken a second order delta sigma modulator, all right, and I put in a DC input, just for kicks I just chose 3.1415, there is nothing holy about this, okay, and I plotted. So which is the input you think, the red one or the blue one? The red one is the input, and what is the blue waveform? This is y, this is u, and as you can see the input to the quantizer is you can think of it as some noise process riding over DC input, and the quantized output of course will have only discrete levels. In this particular example I have chosen a quantizer with delta equal to 2, all right, and the levels going from 7, 5, 3, 1, -1, -3, -5 and -7. How many levels are there in the quantizer? It is an 8 level quantizer with a delta of 2. Okay. So when I put in 3.1415, the output, no, the average of the output must be 3.1415. So it makes sense that the output is hovering between 3, 5, 1 and occasionally 7, all right, and on the average it seems likely that the output voltages of the quantized sequence is 3.14. Okay. Now as I said, this is y and I found ydc, which is simply the mean value of y. Okay. What is the mean value of the output V? It will be must be the same as u, 3.1415. So what I did was found the least square solution to, so ydc n1 times k1 k2 equal to V. So I found k1 and k2, all right. So K1 turns out to be 1.0014, K2 happens to be 1.0037, and why do you think this makes sense? Or does this make sense at all? I mean, why? I mean, see, please note that when you are when the input is 3.1415, are we saturating the quantizer at all? The quantizer steps are from -7 through 7 with deltas of 2. We are well within the linear range of the quantizer, and this is a delta second order delta sigma, right. So, the variance of the noise is not too high, correct. So, we are not presumably saturating the quantizer, right. So, in other words, since we are not saturating the input to the quantizer and the input to the quantizer is busy in the sense that there is some activity, the output should be approximated as input plus quantization noise, where this quantization noise is uniform and white and all this other stuff, right, as you have seen in your assignments, right. If the input is busy, you will have this linear additive noise assumption is close to being valid, okay. So, I mean, so the average gain for the signal for DC is the same as the average gain for noise, because you are not saturating the quantizer. So, it makes sense that the two gains are very close to 1. This here represents what do you think? What sequence is that? No. Look at the red sequence. Red sequence. What levels does it take on? Yes, so what might that be? Is the output of the quantizer V. Okay. What is U? I mean, sorry, what is the blue, the sequence in blue? The blue sequence happens to be K1 times YDC plus K2 times N1. Okay. All right. So, this is the best fit to the quantizer output. And how do you think I got that? How do you think, I mean, or can you suggest a way in which I can get this? How do I get N1? How do I get N1?
In the operation, observe the waveform at the input of.
Yeah, so during operation you observe the input to the quantizer Y. From this you can get YDC. That is simply the average value of Y. How will I get N1? Yes.
Minus YDC.
So, N1 is simply Y minus YDC. Okay. All right. And I know the output V. So, it is quite straightforward to find K1 and K2. It is simply the least square solution which makes the fit the best. Okay. So, k1 times ydc plus k2 times n1 is the blue curve shown there. Clearly there is some error and this is the error. I went and computed the mean square value of E. What do you think the mean square value of E is? What do you think the mean square value of the error will be? I mean, if the quantizer is not overloaded, the output of the quantizer can be represented as, how can you relate the output of the quantizer to the input? Pardon?
Input plus some noise.
Input plus what noise? Quantization noise. So, what is the mean square value of that quantization noise? Delta square by 12. So, what do you expect the mean square value of this noise to be? No, what is the difficulty? I do not understand. You just said it right now. What and why can't? See, the output is nothing but input plus, I mean just now think of the quantizer, you have some input which is busy, the output is a quantized version of this, the quantizer is not overloaded. So, the output of the quantizer is nothing but input plus quantization noise, correct, and of course the output is, I mean, so the output we are saying is we fit it to k1 times ydc plus k2 times n1 plus E, and k1 and k2 are both close to 1, the input to the quantizer is ydc plus n1, correct. So, what must the mean square value of E be? Delta square by 12, and what is delta here? 2. So, what is delta square by 12? 1/3, right. You understand? All right. So, we will continue with this in the next class.